So let's get started on 14.1. And also, by the way, the unit binormal vector is a unit vector when you cross to those two unit vectors, t and n. But anyway, I wanted to clarify that a little bit. Okay, so chapter 14 gets into basically differentiation or partial derivatives. First, we'd start talking about functions of several variables in 14.1. So we go through the definition, kind of how you're mapping a region, region R in the xy plane to a real axis, like the z-axis essentially. So we've already at this point looked at functions of several variables. We just didn't really say it at that point. So some examples would be these: f of x, x squared plus y squared. So parabolas, paraboloids. We also looked at something that's not a function. So I didn't put this down here before, but not a function. Maybe I wrote it on the board. I don't know. Would be like a hyperboloid of one sheet or two sheets or whatever. So something like this. Clearly not a function. Basically, you take a vertical line like that, and you can see it's going to cross those two spots. So just like a definition in single variable. Okay, so then we went to finding the domain and sketching it of two variables. So make sure these are definitely types of questions you want to be able to do. Sketch the domain in 2D mostly. Okay, so go through all those. This was an example of domain in three variables. So this is a four-dimensional function, meaning that the graph is like 4D, but the domain is in 3D. So the domain would map basically this unit ball, and it includes the boundary because of the or equal to here. And so it would be that mapping to another real axis somewhere. Okay, then we talked about level curves. So just know all these basic concepts so far. For level curves, the spacing here, move that down. Okay, the spacing here needs to be equal, and then you get your level curves. But in a picture like this, and this, the books have better drawings, but the steeper it is, so the steepness out here is represented by how close these curves are, and then farther apart or up here, then these would show that it's farther apart. So you're representing basically a three-dimensional picture here in 2 dimensions. So that's the value of it. And then later we talk about how it interacts with the curves. Okay. Right, we talked about a bounded region. So a region is bounded basically if you can put a circle around it that's finite radius. So basically R is finite. These were here just to describe, we're going to be using this notation again. So delta, epsilon delta, and there exists concepts. Could have thrown in for all. Okay, so I think I was just talking about we're going to start using those letters. Okay, we define delta neighborhood. So we use that in all these definitions for open and closed and all that for regions. Abbreviated del n because it takes a while to write that. So this is the delta neighborhood. It's basically we think of it as a small circle, and it's not it's open. So it does not include these little points on the outside, which is basically defined by the delta neighborhood later. But that's where this strictly less than comes in. Okay, so we use that. We define interior point. Interior point's basically a point like this, that you take any point, you can always put a circle around it or a delta neighborhood around it. So no matter how close you get, you'd be able to find one like that. And so that's an interior point. Let's see. Okay, boundary point means you're on the boundary means you put a point there, and there's always points inside and outside that delta neighborhood. So it contains both points in and out of the region. Okay, open is basically has to do with interior points and exterior points. So if every point in R is an interior point, so then it's open. All right. Okay, closed means it includes its boundary point. So it's all defined by those concepts. So I'm not going to test you directly on that stuff. It's just all used in the definitions later, is you define regions to be open, closed, etc. Especially in chapter 16 later. So the takeaway mostly for problems is this: be able to sketch the domain and range in 2D. Okay, moving on 14.2. So we back to limits. So this is like, Calc 1 single variable all over again. So back to limits, here is the epsilon delta definition of limit. In Calc 1, I often have students memorize that. You don't need to memorize it, just study it, please. Okay, so basically you can come in on this point and you can get as close to L as you'd like just by making these, getting as close to these circles as you like. So those circles starting closing as you come in on it. I showed you one epsilon delta proof on that. It's very nice. If you're a math major, study that a bit. No specific questions on that for the test. Then we looked at limits. Limits, the initial concept of finding limits, very similar to Calc 1 type stuff. You factor these things and reduce. So you'll have maybe something like that. This one I think I had you work on this one. This one you rationalize, same concept, and substitute and plug in and reduce. This was something in the book they did, and don't only do this if I ask you to do this. Otherwise, you can kind of go astray. But you can change the polar and then substitute in it and evaluate. So it works. I take a look at it for homework, but I wouldn't worry about it too much. Okay, this one, again, just factoring, another example I think I had you do. Factor that completely. Okay, then we get to showing a limit doesn't exist. Okay, so approach on different paths to a limit. So here you're approaching 0, 0, and you basically are picking these paths, let me zoom in on that all approach whatever points in question. So the point in question as you're approaching is 0, 0, right here at the origin. So you approach on different paths, the y equals x, like this, or you can be on the x-axis and then the y-axis, or it could be a parabola like this. And what you're doing is you're showing that different paths give you different limits. If that's the case, then the limit doesn't exist. So always remember, the two-path rule only shows D&Es, only non-existence. I think I probably wrote that here. To show the limit does not exist, we use the two-path rule. So you only use a two-path rule to show a D&E. Okay, so we did a couple of those later, I believe, maybe on the board. Okay, so expect both of those. Expect one that's factoring and or one that's rationalizing, and or one or two that using a two-path rule. And don't forget to conclude properly here. By the two-path rule, the limit doesn't exist. So you're showing two different limits for two different paths, and then conclude properly like that. Okay, defining continuity. Basically, same definition as single variable, and these three examples here is for single variable, same concept we used. And then 3 is really the same in single. This is, if you can show this, it's assumed that this exists, and then the limit exists, and that they're the same. That's really what you need to show. And it's used for other proofs later, actually. Okay, so moving on. 14.3 is on derivatives. So this is on partial derivatives, as we describe. So first, this is just pertaining to single variable. Showed you the concept again, using those two different limit definitions, or just the way it's defined. So you're approaching x as h approaches 0, and you're getting the slopes of these secant lines, like that. And as you take the limit, you get the slope of the tangent line. Okay, so it's very similar in how it's defined in multivariable stuff. And we went through all this stuff. I'm not going to go through this in detail right now. In Calc 1, I'd always have students use the definition to show a limit. We're going to go right through that, nothing specific. Be able to take partials, because there's a lot of work to do ahead in just partials. So, okay. So I'm not going to ask you just like take the partial. Like you're going to be doing, second partials tests and all that. So, but just practice it. Make sure you know how to do all that stuff. And of course the higher order partials, mixed partials. The takeaway here, just, always know this theorem, mixed partials are equal of any order, right? So know that. Then we got to the geometric interpretation, and it's basically this slope of the tangent line in the direction of the partial. So partial Fy, slope of the tangent line in the y direction, so that direction. Partial Fx, slope of the tangent line in the x direction. Okay, so know what that basically looks like. This is, I guess, a possible example. This is a question I could have. Just find the slope of the tangent line, and you're applying it to the function. Okay, definition of differentiability. Now, this is where this book we're using, Thomas, doesn't do this a lot. So I have posted on Canvas now the extra problems that we did for this definition. So I want you to be able to still do that, like this example. So do this example, very similar. And make sure when you're doing this definition, it's really the format. The format has to be almost perfect. It has to say exactly how this is being stated. The whole thing. Okay, and I gave you another one you did here. I think I looked over that. So be able to do those. It'll be very similar. Okay, moving on. This is same as single variable stuff. Differentiability implies continuity, but not vice versa. The converse is not true. So nice smooth curve implies it's continuous, but if you get like a cusp or corner, it's continuous but not differentiable. So the same thing holds in 3 dimensions or higher. You get those, you could picture this being a cusp, but it goes in all directions maybe. And so it's not differentiable at that point. Okay, and then we went through that proof. I wouldn't ask you specifically this proof, but take a look at it, study it. I could ask you something, portions of it, understand it. I'm trying to get you to look at that. The nice thing about this, though, the sufficient conditions for differentiability is that Fy and Fx, I said that in the wrong order, those two are exist and continuous. So if they're exist and continuous, then it's differentiable. That's really the nice thing. So it's all you have to look at. 14.4, the chain rule. So in 14.4, we define the chain rule. This is all single variable stuff here. Then we looked at how to apply it. So I'm not going to go through all these details. You need to know do all this stuff. You'll see on the sample exams, I basically gave you a slight application of it. Show some things. What did I say in the sample exam? I said I defined harmonic, and then you took a couple partials, and you have to use chain rule, that kind of thing. So there's a few examples like that. So be able to do all these questions, basically, we did here. probably something specific. I'll just ask you, find the partial, possibly. This was the implicit formula. So here, where'd it go? Okay, so find dy dx of this, so you have to do that implicitly. So you differentiate, so it takes all this work. And then right here, we defined the formula for it and applied it. So you don't really have to know the formula. I would more want you to be able to derive the formula. I think I have asked that before. I'll set you up a bit and then have you work it out. So that's a possible one. Okay, and here, this, once you know the formula, then it's like a two-step question. So you have all this versus all of this once you derive the formula in using partials. Okay, moving on, 14.5. Okay, so directional derivatives and gradients. So this is when we define the directional derivative here, and remember, you got to unitize the directional, which you're going. So this could be kind of specific. If I want, you can use cosine sine to just point in the direction using that formula. Probably comes up in the book a bit. Okay, so just know that concept. You have this direction, and then to apply the formula, you have to have the A and B of the components of U be a unit vector, or the sum would be a unit vector. So that's the concept. So this could be a type of question, just something simple like that. So know that concept. Then we got into gradient. We talked about the del operator and the gradient. So all of that. Okay, so know how to do the gradient. Mostly applications later. We get to that in Lagrange multipliers and a few other things. So just don't forget, okay, so this question here, find the gradient, find the directional derivative, right? So you got to unitize PQ. So know how to do that process. And then I did a couple examples. Know this concept, this theorem. So know how to do this theorem. Let differential, so be able to explain this idea here. Gradient of f points in the direction of the maximum increase. So know how to describe that. And it's based off of this formula, the formula back in chapter 12, or the dot product between two vectors. Okay, so be able to do this proof and understand it. May not be asked directly like that, but just definitely important concept. Then examples. Okay, next concept was this. You don't need to know this entire proof, but know the pieces of it. Know the concept, the pieces of it. And of course the theorem itself. If f is differentiable at a point, and of course that's just hypothesis non-zero, then the gradient of f is normal to the level curve through the point. So here, so this is the gradient, and it's perpendicular at all of those places. So if you're over here, let me change the color. You're going like this, then that is perpendicular at all of those intersections. So what you do for the proof, just a quick explanation, I guess, is you look at r prime here, and you show that r prime and the gradient is the dot product is 0, right? Then you know it's normal. So that, and it's all in the setup. It's all in the setup constant and how you go through it. And then the key later is, again, chain rule. That's why I always go through this one, because you're doing ddt of f, but x and y are functions of t, right there and there. And so you got to use chain rule, and then when you basically factor that, you get the gradient in r prime, and that's equal to 0, which means, of course, it's perpendicular. So I want you to study this as well. no pieces of it. And then we'll see what I come up with, basically. Okay, 14.6, tangent planes and normal lines. Okay, so this is all the example and derivation. I'm not going to go through all that. Let's just go to the definition. So you need to know the definition, how a plane is defined. So if you have a function set equal to 0, so like this, and we'll go look at that down there later. Then you do its gradient, and then that is the normal vector. So you have some surface, so this is my surface S. When you do the gradient of F, then you get this normal vector N. Okay, so once you do that, then that becomes those components for your plane. Right, because the definition earlier we did, this was like your A, B, and C of N. So that's not your A, B, C, that's your normal vector. So be able to determine that plane and line, essentially. Okay, now we're getting into the latest stuff I just left you with before all of this. Extreme values and saddle points. So this basically... you can look all through this stuff, extreme values and such. But basically, you need to apply the second partials test. So we did a few of these, second partials test. Make sure you can do all that. That's a guarantee. You're guaranteed to have a question like that. This was from an example I did in class. Don't need to really look at all that stuff. That was just something I wanted to show you. So again, we did all those. If there's a few points, do some sort of chart or something, some sort of setup describing. Just read what I say. If I ask you for the actual point, then get the actual point. Otherwise, just find the XY value. Just read it and answer it appropriately. Then there's definitely an application question. We did a couple of those, like this one, and then we did the volume one. So there's going to be something. I don't know what, but there'll be something with an application on it. Usually the more difficult question, but you need to have the setup. The key here was, what are you maximizing or minimizing? So for this one, actually, let's go back to this one. So for this one, it says... positive integers whose sum is 1, and the sum of the squares is a minimum. So it tells you what the function is that you're maximizing or minimizing. Here are the sum of the squares. But this has 1, 2, 3 variables. Our second partials test only is used with 2 variables. So you need to take your, basically your constraint, which was the sum is 1, solve, and substitute in. It's a standard, look to them. And then let's go back to this one. Find the volume ellipsoid. Okay, so that's just an ellipsoid. Here's the volume. For a fixed sum, show that the ellipsoid actual volume is a sphere. So what you're maximizing is volume. So this is what you're maximizing right here, the volume. So again, 3 variables, solve one of them, and substitute in. All right, and what you're using then is that fixed sum. That's why it kind of told you that. You can do this question and let k be 1, and it still works out. But I used k just to be, this is what it said. So the fixed sum is arbitrary. Okay, so something, there'll be definitely something like that. Okay, and then this would do another example. And then we went on to Lagrange multipliers. So for Lagrange multipliers, again, know that process. We don't go through all those details. Basically, you got to do these. You got to set up this system of equations. Do the system. Let's just go to the example. So you set up the system here, here, and here. Make sure your possible zeros satisfies the constraint as well. And this one, remember we did this one where 0, 0 did not satisfy the constraint, so it's not a possibility. Toughest part here is solving the system, frankly. Once you have the system solved, then it's easy. all you got to do is plug in the values here, here, and here, and see which one is max or min. And then you just state it. So just be organized like that. There will be a Lagrange multiplier, something similar to these we got to solve. Okay, I think that's it. More